Welcome to another video of CS360, and this time we will talk about time and space bounded computations. Oops. Okay, let's fix the handwriting. Okay. So until now, we've basically discussed Turing machines that have unlimited time and space. I mean, of course, computations were always assumed to be finite. So, you know, of course, a computation was not allowed to take infinite time. We would say a machine loops and does not terminate in that case. You know, but if a language was decidable, that would give you no guarantee on how quickly it was decidable, or how much space, how much of the tape the Turing machine had to use in order to decide this language. Okay, so in this last unit of the course, we are going to talk about Turing machines that are bounded in time or space, or other well, primarily time or space resources. We'll also talk about non-determinism as a kind of an additional resource in a future lecture. Okay, so to do that, we first define. So this unit should be a bit more intuitive because it's a bit closer to the type of computations that we're used to seeing in, you know, other classes. You might have seen in programming classes or algorithms classes, the notion of computational efficiency, space usage, time usage, and so on. But we want to define this formally. So in other classes, it sort of often would be hand-wavy what it means for a computation to take a certain amount of time. Here we have mathematical definition of computation. We have a Turing machine. We define that extremely rigorously, you know, as a 7-tuple of things, you know, states and so on, transition function. So, okay, so we have this formal definition of Turing machine, and we want to turn this into a formal definition of what it means for computation to be efficient. Okay, so the reason to be formal is that then we'd be able to prove things. So we can, you know, think about trying to prove, for example, whether we can solve more tasks using more time. If you had larger time budget, can you do more things? Are there, you know, or are there exceptions to this? You know, and maybe we would even want to say that, okay, a certain specific task, a certain specific language cannot be computed efficiently, even though it's computable, it's a decidable. I mean, it's not decidable efficiently. So, you know, that this is various things that we would want to formally prove. And of course, to formally prove, we would need a formal definition. So this is the point of this last unit of the course. We will formally define resource-bounded computations and prove a few things about them. Okay, so first, so given the Turing machine M, we will need a notion of its running time and a notion of space usage, which I'm going to call the space function. The space function. But these are basically analogous to each other. One is how much time M is going to use, and one is how much space M is using, okay? Now, of course, that depends on the input. So we have to be a bit careful about how we define these things because it varies by the input of M. Okay, so the way we define it is for any W, okay, we can let T of W be a number of steps M of W takes. And then we can let S of W be you know, number of cells of the tape that M of W steps on. It doesn't really matter if we define it as steps on or writes in. It's not going to make a big difference for us. We're just going to assume here that if M steps on some cells in order to write something further than those cells, then that counts as having used those cells. Essentially, it's like it's as if it's at least looked at them. So okay, so we will define this S of W is the sort of the number of cells of the tape that M of W ever saw in its computation when it ran on W, right? So now these are numbers. You know, we can put, you know, so basically, for these things, we will just set it to be equal to infinity if M of W in fact loops. Okay, so here T and S are functions with signature. That's sort of like it's sigma star. Sigma will often be 0, 1, but we'll just leave it as sigma star. And it maps sigma star to either a natural number or the symbol infinity. Okay, so basically the output of T of W is either a natural number or it's infinity. That's how many steps M takes on input W. We will usually only talk about halting Turing machines, but we will allow it to be infinity in case we have a machine that doesn't halt on some input. Okay, so then this is a definition of the number of steps that sorry, the time and space usage of M on a single input. But we want, so what we'll be interested in is how this time and space requirement of M grows asymptotically as the input gets larger. Okay, and to do that, we have to talk about you know, we have to convert from talking about specific inputs to talking about the input size. So what we'll do is we'll set little t of n to be the maximum, you know, of t of w over w, such that w is at most n. Okay, so t of n is the maximum running time that m ever takes, right? Not maximum number of steps m ever takes on any string w of length at most m. That's t of n of length at most n. Yeah, and similarly, little s of n is going to be the maximum space that m ever takes on input string that's at most n long. Okay, so these are functions of the input size. Okay, so for any Turing machine, we can define this time and space functions like this. And note that the way they're defined, then they're going to be non-decreasing functions. They're basically weakly increasing, both of them. So as the input size get larger, this time and space, the way I've defined them here, have to at least not get smaller. They are larger or equal to what they were. They may equal infinity if m ever halts at some point. But you know, if m actually decides a language, then these will never equal infinity for any given finite n. Okay. Okay, so that defines T and S for one Turing machine. Now there's a few. Okay, so a few more details here. So one thing is that, you know, the exact definitions of T of n and S of n, the exact definition of the time and space functions depends a lot on the details of the Turing machine implementation. Like, you know, it depends on the alphabet size, and depends on one tape versus two tape. It just depends a lot on junk like this. So one thing we will do to try to be a little less sensitive to the implementation details, or like, for example, another implementation detail is how we encode the input. You know, often our input looks like an encoding of something, like an encoding of x and y or something of a pair. How exactly did we encode this? What did we have a separator symbol here? You know, the details of these encodings might change T or S by plus or minus 1 or 2, maybe even by a factor of ×3 or something. So what we will do is we will use big O notation to ignore all these constant factors. Okay, so you may have seen this before. So basically we say that f of n is equal to big O of g of n, where these are functions, if basically f of n is less than or equal to a g of n plus b for some, so basically if so basically, if there are fixed a and b such that for all n, this holds, then we say that f of n is O of big O of g of n. Okay, so you probably have seen this in other courses. There's a bit more detail in the notes if you haven't. One thing to remember, though, that's maybe sometimes not emphasized in other courses is that the big O notation is actually kind of stupid. So when we write equals big O of something, what that really means is less than or equal to big O of something. Okay, so it's basically equals big O behaves like a less than or equal. Okay, if you wanted to write greater or equal, you would write equals omega. Okay, so this is really stupid notation. So f of n equals omega of g of n. Okay, is sort of like saying greater or equal. Okay, so big O is like saying less than or equal to. Big omega is like saying greater or equal to. Okay, and there's other ones, like if you want to say equal to up to constant factors, so in other words, both big O and big omega, then I would write f of n is big theta of g of n. Okay, so I didn't come up with this notation. Okay, so it happens to be standard, unfortunately. But this is often people forget about this. Big O does not mean the same thing as big theta. So when we say something is big O, like if I tell you a computation is big O of n squared, that doesn't mean it takes exactly n squared up to constant factors. It actually means at most. So technically n is O of n squared. Yeah, like if it takes n steps, then this is big O of n squared. Right? So if you want to say that a computation takes actually n squared of the constant factors, like I actually want to claim it's n squared, I should be saying big theta of n squared. Okay. So this is the notation as is standard in not just computer science, but actually broader math. Like you have number theorists using this notation, and it predates computer science, this notation. Anyway, it's pretty terrible notation, but you know, it's not my fault. Don't blame me. So okay, so equals big O means less than or equal to. Equals omega, big omega means greater or equal to. And equals theta means actually equals. All up to constant factors. In all cases, we ignore constant factors. Okay, and we less common but still occurs. Equals little o means strictly less. Okay, and then equals little omega. I don't know how to style an omega here. Equals little omega is strictly greater than. Okay, so these are the strict versions of the big omega and the big O. Okay, so the little omega and little o are strict inequalities. And the formal definition is in the notes. Okay, so then with that in mind, we will define our first few complexity classes. So, so for a function f from the natural numbers to natural numbers, we will let time, the time of f of n. This is going to be a complexity class. It's a class. By the word class, we usually mean a set of languages. So a set of sets of strings, right? So this is going to be the set of all lang A, such that A is decidable by a TM with runtime. With running time, T of n, which is big O of f of n. And remember, that means less than or equal to up to constant factors. Okay. So at most. Okay. So that is the time. It's a class of languages, a set of languages. It's a set of all languages that are decidable in time at most f of n, except for constant factors, which we don't care about. Okay. So at most 100 f of n is fine in terms of time. Okay. So that means that to decide if, so suppose that A is in time f of n. Okay, suppose I have A that it's in time f of n. Then to decide A, if I want to know is W in A, question mark, then what I need to do is, well, there is some Turing machine M, or maybe M sub A. I can run it on W. Okay, and the time that it will take, is big O of f of the size of W. And again, it's like at most, right? Like I mean, I want technically the way it's usually written is equals big O of this, but that literally means at most. It means less than or equal to. Okay, the notation is terrible. Okay, so so that's what it means. There is a machine M sub A, which decides whether the string W is in A. Okay, it answers this question. Okay, so of course, in particular, A must be decidable. And the time it takes is at most big O of F of the size of W. So we care about the size of the input string. Okay, and it's important to remember that we always care about the size of the input string and not about any other properties of the input string. This can be a bit weird sometimes. Like sometimes if you artificially increase the size by just padding it with a bunch of zeros at the end, then that actually affects the running time in the sense of the machine, because the time is always in comparison to the input size the way we defined it. Okay, but that's the accepted formalism, and it's the weirdnesses are not too bad. So it's just something to remember, something to keep in mind. Okay, so this is time, and we can do the same thing with space. So space of f of n is the set of all languages such that A is decidable by a TM with space function whoops, s such that s of n is big O of f of n. Okay, and again, this means less than or equal to, right, up to constant factors. Okay, so this is space. So space is everything that's decidable by a Turing machine, that any language that can be decided by a Turing machine that uses at most f of n space on inputs of size n up to constant factors. And time is the same thing, but the Turing machine has to take time at most f of n up to constant factors. Okay, so one thing to note is that time of f of n is a subset, it's contained in, it's a subclass of space. Whoops, space f of n. And this is for all f, yeah, it doesn't even depend on f. Why is that? Well, because you know, suppose we had A that's in time, so we want to show that A is in this space class. Okay, so we have this A, and because A is in this time class, then we know that we have a machine MA which takes at most O of f of W time, so steps, to decide whether W is an A. Okay, so it halts within this much time, which is this many steps of the Turing machine. Okay, but in each step, you can only step on one new tape symbol. Okay, so if you're using only this many steps in this computation of MA of W, then you looked at only this many tape cells. And by definition of space, you only took at most this many space in your computation of MA of W. So then immediately the space function, in other words, I'm saying the space function for a given Turing machine is always at most the time function up to constant factors. I should put a big O somewhere. It's up to constants. Why up to constants? Because maybe there's a +1 if you started for free on some tape cell, then I guess it's a free +1. We don't care about that. Okay, so so then you know, the time function is bigger than the space function. So if this machine has time function at most this, then its space function is also at most this. And therefore, A is in this space class because it's decidable by a machine that uses at most this much space, okay, at most f of n space, whereas n is the input size. Okay, so the time class is a subclass of the space class. Okay, now another thing is that actually this time of f of n It actually depends on the definition of a Turing machine, and it depends on whether it has 1 tape or 2 tape, the Turing machine, or 3 tapes. It actually is a bit sensitive to such details. Why? Because we care about whether the number of steps is O f of n, steps on inputs of size at most n. But how many steps a Turing machine can take, even though these machines can simulate each other, so a 1-tape Turing machine can simulate a 2-tape Turing machine or a 3-tape Turing machine, how many steps does it take to do that simulation? And the answer is not necessarily the same number of steps, maybe slightly larger. Maybe at least number of steps times log number of steps, or maybe number of steps squared. Okay, we didn't go through the proof of how many steps. As it turns out, it's not that much more. Okay, so it depends on what you're trying to simulate exactly. But all the conversions, we said all these Turing machine definitions are all equivalent. If you enlarge the tape alphabet, you get something equivalent. If you add tapes, 2 tapes, 3 tapes, that's all equivalent. Assembly language is equivalent to Turing machine. We had all these arguments that things are all equivalent to each other. Okay, but those arguments didn't talk about the overhead of the simulation. How much slower is it to simulate a 2-tape Turing machine with a 1-tape Turing machine or any other conversion? So now we suddenly care about efficiency. We suddenly care about the runtime. And it turns out that these things don't have to be equivalent, but they're only slightly inefficient. So simulating a 2-tape Turing machine by a 1-tape Turing machine, I don't know exactly what the overhead is, but it's at most quadratic for sure. Okay, so you don't need that much more steps. Okay, and similarly for change of the alphabet size for the tape alphabet or assembly language versus Turing machines, all these things. Usually the conversions are only log overhead if you try really, really hard to optimize them. But I don't want to go through the proof of that, and I'm not even 100% sure that holds in every case. So let's not do that, and instead just say it's most quadratic or cubic. Okay, fine, but that still means that this time, like for example, time of n squared, something in n squared time, the class of all languages decidable in n squared time. That definition is not robust to whether we mean decidable in n squared time on a 1-tape Turing machine or decidable in n squared time on a 2-tape Turing machine, because there might be a difference of at least log n between the two, maybe a difference of squared, maybe, maybe a quadratic difference between the two models. So, this feels like a very non-natural, non-robust thing that depended on exactly how we defined a Turing machine. So to remedy that, we're going to kind of sort of combine a bunch of classes into one giant mega class, and we will call this P. P is going to be the union for, over all k equals 1, 2, 3 of time n to the k. In other words, this is time n union time n squared union and so on, time n cubed, time n to the 4. Okay, so of course these classes keep getting bigger. So time n squared contains time n already. All right, but we're taking this infinite union that just says, okay, a language is in P, A is in P. Okay, basically now means that there exists, it's equivalent to saying that there exists K and N such that A is in time n to the K. So in other words, A is decidable in polynomial time, A is decidable in O n to the K time where n is input size, and K here is a constant that's not dependent on the input size. Okay, so so basically P is all the language decidable in polynomial time. And now this is actually robust to how we define a Turing machine. So now, because all the conversions are only kind of polynomial and overhead, you have to trust me on that one, or you can go back and go through all the conversions and verify for yourself between the conversions between a 1-tape Turing machine and a 2-tape Turing machine and so on. They all take at most polynomial overhead, and because of that, the class P is the same whether you define it in terms of single tape Turing machine, two tape Turing machine, three tape Turing machine. Doesn't matter what the tape alphabet is, as long as it's large enough. As long as at least let's say you have both 0 and 1 in there. It doesn't matter what even whether you're a Turing machine at all versus assembly language or something, as long as you define that rigorously enough. So P is kind of like a very robust and very well-defined class of languages. Okay, it's a fairly natural class. And we will consider it to be the class of languages that are efficiently decidable. So the things in P, computations in polynomial time, we basically think of them as efficient. And anything not in P, we basically think of as inefficient. Okay. Okay, so that is the class P. We can, of course, do the same thing for space. So we can say, okay, the space definition turns out to be a little bit more robust than time in practice. So it's not as, like usually the conversions actually don't lose much space overhead. But why not? Let's just in case, let's define PSPACE to be a more robust version of the space classes. So it's going to be the union for k equals 1 to of space n to the k. So basically, A is in PSPACE. A is in PSPACE is equivalent to saying that there exists a natural number k such that A is in space n to the k, i.e. O n to the k space is used. So A is decidable in O n to the k space, where n is the input size here, and k is a constant that's not dependent on the input size. Okay, it's only dependent on the language k, on the language A, but it's not dependent on the input that you give to the machine that you're asking whether this input W is in the language A. Okay. Okay, so this is PSPACE, and because each time class is a subclass of the corresponding space class, we actually get that P is a subset of PSPACE. Okay, so P is a subset of PSPACE. We can keep going. We can define exp. We want this to be exponential time, so we can just, you can imagine doing 2 to the n and 3 to the n, 4 to the n, and so on. But actually, the way it's usually defined in computer science is an even larger class. It's time 2 to the n to the k. So it's 2 to the n squared, 2 to the n cubed, 2 to the n to the 4. It's the union of all of those. So, A is an exp. That is equivalent to saying that, that A is in, that there exists k such that A is in time 2 to the n to the k. So for example, if A is computable in time, decidable in time 2 to the n to the 100, that's considered exponential time. That's considered in exp. Okay. The notes also talk about a class E, which is a subclass of exp, where you only have like 2 to the O(n) kind of time bounds. Okay, and we can do EXPSPACE as well. EXPSPACE. Okay, and that means what you think it means. It's the same thing. It's the same thing as X, but just for space, or the same thing as PSPACE, just exponential with exponential function here, like 2 to the n to the k instead of n to the k. All right. Okay, so maybe the next thing to know is that PSPACE is actually a subclass of exp. Okay, so we can actually write this chain like this. Okay, so the time class is always a subclass of the equivalent space class with the same bounds. But the space is a subclass of exponentially more time. So if you add exponentially more time, then you get something bigger than the space class. And you can keep going with this chain, like you can do exp here, the double exponential things. So you can keep going. There's no limits to how far you can go. Get larger and larger classes. Okay. All right. So so how do we prove this containment, right? So why is this true? And the idea is, okay, so suppose you have A that's in here, that's in P space, right? So that means that A, in fact, is in space. It's in space n to the k for some k, right? Like there exists a k. A is decidable in a way that uses only O of n to the k space, right? Like let's say it uses only 100 n to the k space, so of inputs of size 100. Right. Actually, let's give this Turing machine a name. So it's called MA. So MA of W uses at most, 100. This constant 100 might be a different constant, but at most 100 W to the K cells of the tape that it's looking at before correctly deciding whether W is an A. Okay. And so the claim is that the claim is that MA of W uses only something like 2 to the O W to the K steps. So exponentially more steps than the amount of space. So it used like O of W to the K space. But we're claiming it only uses at most exponentially more time than that. Okay, so if we can prove that, then of course that would mean that MA also shows that A is an exp by the definition of exp. Okay, so we just need to show that if a machine when run on some string uses it, if a computation uses at most a certain amount of space, then yeah, it can use more time than it uses space, but only exponentially more, not more than exponentially more, not like double exponentially more. That's not possible. Okay. Why? This is basically because we know that M of A halts on W. Okay, so that's because M of A decides A. So M of A halts on W, and it uses at most as much space. And there's only, so if you can imagine a section of the tape, and there's a section of this tape, and M of A, when run on W, it never leaves this section, right? So it never crosses this these boundaries. So in theory, the tape might continue, but M of A will never go there. It will stay locked within here, right? And M of A also has the internal states queue, like a set queue of internal states. That kind of DFA-like thing where they link to each other, right? It has a head, have these internal states inside the head. Right, but the point is that this this whole thing will only be like 100 W to the K long, like this region here, and there's only so many ways to have a configuration on this region. So imagine all the possible different ways that the machine can be configured, all the different configurations of what the machine could look like, how this tape is filled. Okay, so how many ways are there to fill the section of the tape? Actually, there's gamma. Sorry about that. Okay, so how many ways are there to fill here? There's size of gamma waves to fill one cell, where gamma is the tape alphabet. And so there's gamma to the 100 W to the K ways to fill the tape. And then there's only so many ways to have an internal state in the tape head. There's only like Q ways to have that. And there's only so many positions that the tape head could be in. There's like something like 100 W to the K ways of being in different positions. And the thing is, once you run out of positions, if ever in the run of MA on W, you repeat a configuration twice, then you will repeat it infinitely many times. Because if one configuration leads you eventually to return to the same configuration, then if you keep going, of course, you'll return to the same configuration again, because the configuration tells you everything you need to know about the state of the machine. So if the state of the machine causes the machine to enter the exact same state of the machine again, and by state I mean kind of configuration, including what's written in memory, then of course it will enter this loop infinitely many times. So that's not possible because M of halts one around W, because M decides A. So there's this many configurations. We kind of know they cannot repeat, and because they cannot repeat, M of MA one around W can have at most this many steps. And this is actually it's 2 to the big O of size of W to the K. Okay, so you can verify that, I guess, by basically using the fact that the size of gamma here is a constant independent of the input. The size of Q is a constant independent of the input. Okay, and then this is much smaller than 2 to the O of W to the K. So basically, because of this kind of calculation, it follows that the number of steps you can take before you would find yourself in a loop, essentially, is only exponential in the memory that you're taking, but not more than exponential. And therefore, anything in P space is in exp. Okay. All right. So that's the main thing for this lesson. One more thing that is in the notes that I won't really go through here is that if P equals P space, then exp equals exp space. So this was shown in the notes, this implication. And this is kind of by a padding argument. This is basically saying, you know, suppose you have a language in exp here, right? You have a language in exp. Then if I basically increase the inputs to here artificially, like so basically to decide if A, right, to decide if W is an A, I have a machine that takes exponential time to do this. But imagine if I now increase the size of I just pad this gigantically. So I change from W, I change, like I make a new language, not A, let's call it B. And B is sort of like A, it has the same W's in A, but next to each W is like a gigantic pad of zeros and a ridiculously large pad of zeros. Okay, the pad of zeros is so large that although the only kind of information content here is W itself, the input size is now something like 2 to the W to the K instead of being like W. So the input to A had size W, but the input to B, even though B is basically the same language, the input to B is like exponentially larger. Okay, and because the input is exponentially larger, as a function of the input, an exponentially long computation in W looks polynomial in this new input size. So if we did something exponentially slow in W, in terms of this new input size, this looks like it's only polynomially slow. Okay, and so what we get is, because A was an X, we get that, or sorry, I actually meant to say that A is in X space here, sorry. We're starting with the language in X space and trying to show it's an exp, my apologies. So anyway, we still define B like this, and again, because of this padding, if we had a computation that's that uses exponential space, then because of this padding, in terms of the new input size, this looks only polynomial space. Okay, so in terms of the size of W, it looks like we're taking exponential space, but in terms of the new input size, it looks like we're taking polynomial space. And therefore, we get that B is in P space. But because of this assumption, right, we're trying to show, right, I'm just, as a reminder, we're trying to show this implication. So we're assuming the left-hand side and we're trying to show the right-hand side. We don't actually know that either of these sides are true. I'm just trying to show if the left-hand side equality holds, then the right-hand side equality holds. Anyway, so to continue the sketch here, because B is in P space, then B must be in P by this equality we're assuming. And if B is in P, then there's a way to take inputs like this and in polynomial time decide whether, you know, this is in B, which is the same as saying in polynomial time deciding whether W is in A. And so but this is polynomial time in this gigantic input size, which is exponential time in the original input size. And so we conclude that A is an exp. Okay, so this is called a padding argument. It's a very strange and weird argument that only uses these details of how we define these classes, where all the computations are in terms of the input size. And so we can play with the input size by padding it, increasing it artificially with zeros. And then we can convert X space into P space by doing that, by just adding a bunch of zeros. And so if P space equals P, then when we take a language in X space and convert it to a language in P space like that by padding, then that language must be in P. But that means the original one must be in exp. Okay, so so it's sort of due to the way we're defining all these classes only in terms of the input size, all these costs are in terms of the input size. If P is equal to P space, it forces exp to equals to X space. Now we don't believe this is true. So we believe, we don't know if P is equal to P space. We believe no. Okay, and we don't know whether X is equal to X space either. We believe they're not equal. Okay, but we do know that if P equals equal to P space, then X is equal to X space. Okay, and this is kind of a cool fact to know, but also cool is the argument. It's a padding argument. It does show up every once in a while. So it's useful to know this concept of a padding argument. All right, and that's it. That's it for this lecture.